Alright, what I want to do right now is bring you back to our big picture. So if you remember, we're over here in descriptives world, descriptive statistics. We've talked about central tendency, measures of spread outness, and now we're moving on to measures of distributional shape. But before we talk about distributional shape, we're going to take a little bit of a detour and go into a discussion of standard scores and the normal curve. Standard scores in the normal curve are going to be critical as we progress through and into inferential statistics, and then all the different analyses we'll talk about, and pretty much everything we'll do next semester. So this is a pretty important lesson. Not that what we're going to do right now will apply kind of one-to-one correspondence with the future, but what we'll learn here will definitely be applied to the future. So we're going to start looking at standardized scores in the normal curve in a very basic way. The first thing I want you to do is consider if you were in a class and you took some sort of assessment or test. Your score is 81, the class mean is 75, and the class standard deviation is 10. So the question is, how did you do? Well, and by this I mean, how did you do in comparison to the rest of your class? If you're looking at your score, obviously you scored better than the mean, but that's about as much as we can tell. The scores are distributed around the mean on average at 10 points. So, in comparison to everyone else, about how did you do? Well, one way we can figure that out is to look at your score in terms of a standardized score. So we are going to focus on standardized scores because they are useful for describing an individual score in relation to other scores in the distribution. So by looking at standardized scores, we're going to be able to tell exactly what percentage of people you scored better than on that assessment. There are many types of standardized scores. You may be more or less familiar with them depending on your position. So I know some in education or the social sciences, they really work a lot with standardized scores, and other people don't. But we are going to focus on one type of standardized score, and that is this Z-score here. So thinking about the Z-score, see if I can get my pen to work over here. Thinking about the Z-score, we are gonna, where'd my pen go? There it is. Okay, so thinking about my Z-score, first of all, we're gonna take a look at the formula and kind of what it means. So I do know that Z-scores always have a mean of 0 and a standard deviation of 1, and that'll become more meaningful here in a minute. But just looking at the formula for a Z-score, if I have a Z, that is going to be equal to my score minus the mean divided by the standard deviation. So you can kind of see how everything we're doing fits together. The mean, we've already figured out. This deviation score we've talked about. Standard deviation, we've got to be able to calculate that. Remember, standard deviation is equal to the square root of that sum of squares divided by n minus 1. Remember all that. So you can kind of see that the progression of everything we've done, we've needed to know how to do that so that we can figure out a Z-score. So if I'm looking at, remember my 81, so that's going to become my raw score, or that is my raw score. I'm going to start calling it my raw score. And I want to convert my raw score to a Z-score. So to be able to do that, I'm just going to follow the formula. My score is 81 minus the mean, which I know from the information on the previous slide. And they also told me the standard deviation, which is 10. All right. So 81 minus 75 is what? 6 divided by 10. Which we know that is 6/10, right? So my Z-score is 6/10, or 0.6. Now, I can compare that here. If the mean of Z-scores are always 0, I can tell that I did better than the mean, right? which I already knew from this information. But what this is also going to do is allow me to say, oh, I scored better than whatever percentage of people who took the exam. Okay? So let's kind of keep that idea in mind as we go along. Z-scores and raw score distributions will be the same shape. Only the scales will be different. So what about when you go to the doctor for the checkup, at least here in the States, and the doctor or the nurse actually puts you up on the scale and they tell you your weight, or you can see the weight on a number, except it's in kilograms, which for me here in America means very little. But then she pushes the button and it converts it to pounds. Aha, now I know whether or not I should be happy or sad with this number. But it's just a change in metric, right? Well, that's the same idea with raw scores and Z-scores. I had my 81 raw score, and I just converted it to a Z-score of 0.6. Okay? So I haven't changed the information. I've just put it in a different metric. Or if you want to think about a measurement that comes in miles, but you need kilometers, or vice versa. Maybe your kid's running track and they tell you they want to run the 1 mile. What is that equivalent to on the track? Well, that's that 1,500 or 1,600, right? Meters, not the 1 mile. Okay? Right, so we're not changing the information, we're just simply converting it to a different metric. So again, the information does not change, it's just on a different scale. Okay, and I've already given you a few examples there. Okay? So let's think about these questions. Let me remind you that the mean of a set of Z-scores, I'm just going to do Z with a bar over it, was always equal to what? Always equal to 0. And the standard deviation of the Z-scores is going to be equal to 1 always. So what is the variance of a set of Z-scores? Well, if I know the standard deviation is 1, how do I get the variance? I just square it, right? Standard deviation and variance. The only difference is the variance is squared. 1 times 1 is 1. So the variance will also be equal to 1. What will a set of Z-scores sum to? All right, well, if you think about it, it should be just like the regular scores around the mean. And we know that those deviation scores sum to 0, correct? We'll do an example of this here in a minute just to illustrate it. If you have n equals 38, so remember that means you have 38 participants or 38 scores. How many Z-scores are there? Well, for every raw score, for all 38, we can convert every score to a Z-score. So if there are 38 raw scores, we're going to have 38 Z-scores. Okay, when you score below the mean, your Z-score will be negative, right? Because if the mean is 0 and we score below the mean, we're going to be below 0, which is negative. Okay? So far, so good? Using Z-scores and the normal curve, we can find out what percentage of scores fall above or below a certain Z-score. But first, let's look at what's the normal curve. Now, in another presentation, I talked a little bit about the normal curve in relation to IQ scores, but the normal curve actually has some very specific characteristics, and again, it's going to become very critical in our study of inferential statistics. So when I say a normal curve, I'm saying the same thing as the data are normally distributed. And again, that is going to become really critical because a lot of what we do in statistics, especially when we get into our different analyses, depend on the fact that our data are normally distributed. So what do I mean when I say the data are normally distributed? It means that the data adheres mostly to the properties of a normal curve. Now, and we're going to go through here in a second what those properties are, but I give this little note here that says mostly, because when we get into inferential statistics, we're going to give ourselves a little bit of flexibility there when we're looking at our data sets. And every time we run an analysis, we're going to say, is this data normally distributed? And we're going to check to see, does it follow the properties of a normal curve? Mostly. It doesn't have to be identical or perfect, but our data needs to mostly follow the properties of a normal curve. Okay, so let's look at them. The properties of the normal curve are that our data is symmetrical. Now, in just the next presentation, we're going to talk about these two things, skewness and kurtosis. And they all have to do with the shape of our distribution. But for our data to be normal, it needs to have, and there's no way I'll be able to draw it perfectly, but nope, not too good. But you've seen the bell-shaped curve. In fact, here I have it noted down here. It's that classic bell-shaped curve. But when you look at a distribution or a set of data, you want to see that it is unimodal, so it only has one mode. And the mean, the median, and the mode are all the same value. So if you can imagine, and don't go by my picture, but picture that perfect bell curve in your head. Ooh, it's definitely not perfect. But right here in the tip top of that distributions curve or hump, however you want to describe it, the mean, the median, and the mode are all right here. Okay? It only has one mode. It's symmetrical. So if I drew a line, a dotted line, and I folded it on the dotted line, the two sides would match. It's perfectly symmetrical. Kurtosis is that height to width ratio. And again, we're going to talk about these more in a little bit. But basically, it has a nice height to width. So it wouldn't be something like this, where it's tall and skinny, or this, where it's short and fat. So these two may have the same value for the mean, the median, and the mode, and they may be unimodal, but it also has to have a normal skewness and kurtosis. So this, even though it's symmetrical, and it that's terrible, even though this is symmetrical and it probably meets all of these, same with this one, a little better dotted line there. So even though it's probably symmetrical and it may meet these requirements, it's not going to have that, it doesn't have that nice height to width ratio like this one does. Okay, and we'll get into more of that in just a little bit. And so I'm going to say this is a no, this is a no. Our normal curve has that nice bell shape. All right, so z-scores are useful because we can describe, as I've said probably 5 times already, the distribution, our score, in comparison to other scores in the distribution. We can do that by looking at a table in our book and describing how they fall relative to or on the normal curve. All right, and so before we get into that activity, what I want to do is just remind you, okay, remember how we were talking about those IQ scores? And I only use IQ because most people are relatively familiar with IQ. Remember we said they have a mean of 100 and a standard deviation of 15. 1, 2, 3, 1, 2, 3, and plus or minus 3 standard deviations. Captured what, about 99.6% of people, right? So we said 99.6% of people have an IQ that ranges from 55 to 145. So that gets most everybody. And IQ scores are really normally distributed. Again, forgive my drawing. But we could look at those percentages under the curve, right? And start to figure out how many people are in each segment of that curve. Remember we said there's like 68%, and then if we add one more standard deviation, that gets us up to what, like 95%, somewhere around there. And then if we add those last two areas, that's where we get up to that 99.6%. Okay, does that ring a bell? All right, well now, if I'm looking at my 81, which on this would be like probably about, see if I can do it without it erasing my dot, but it's probably going to be about right here. Nope, I don't know why that keeps happening. But what I can do is I can figure out how many people, if my 81's say about right here, I'll just color in all this, I can start to figure out what percent, which is this, so this is my question mark, what percent of people did I score better than right here? It doesn't like me making small marks. Okay, so what percent of people did, that's a terrible drawing, but hopefully you can tell what I'm doing. What percent of people did I score better than? All right, so rather than these real general 68, 95, 99%, if I convert my score to a z-score, then I'll be able to figure out exactly what percent. And I do that using an appendix in the back of the book. I think this was for a different text. So the book we're currently using, let me grab it real quick. So the Salkind Statistics for People Who Think They Hate Statistics, that table, let me get the exact page for you. It is page 400, and it's Appendix B. All right, so instead of this, it's actually Appendix B, and it's on page 400. All right, so what I'm going to ask you to do, if you don't have your book, while I get ready for the next stage of this recording, go ahead and get your book and find Appendix B on page 400, and the name of that is Areas Beneath the Normal Curve. All right. Okay, I will catch up with you in just a second.